Hi, my name is Emmanuel Tukudo and I'm currently taking Physics 2211 at Georgia Tech. This is my lab report on the motion of a falling object. Our system here will be a paper ball and the surroundings will be everything else. The lab discusses four key topics. The first being Newton's second law, which states that an object's acceleration is dependent on the net force being applied to the object and the mass of that object. Velocity, which is the time rate of change of displacement of an object and its unit is meters per second. Drag, which is air resistance or how much air or another medium that an object is traveling through pushes back on that object. In this case, it's going to be air resistance, which is pushing upwards, and gravity, of course, which is a force that pulls all objects towards a mass, in this case, Earth. The purpose of this lab was to use an object and demonstrate the motion of the falling object while monitoring other forces acting on the object. In this lab in particular, we'll be examining both the drag and gravity as the paper ball is falling. So on the right, we have five equations which we'll be using: Newton's second law, the velocity update formula, position update formula, force due to gravity, and the drag force formula where we'll be using a proportional constant B, which you'll be seeing later in our computational model. On the left, we have a diagram of drag force and gravity acting on an object. As you see, the first model has the ball just being released from rest, so only gravity is acting on it. In mid-air, the ball has gravity and drag acting on it, but gravity is stronger. The last model has gravity and drag force being equal, which means that it's at terminal velocity when air resistance and gravity are the same thing, and the ball never speeds up or slows down. Now, what you are seeing is the first part of the actual lab experiment. It's a video of me dropping the paper ball, which I recorded in Tracker. As you can see, as the ball is dropping on the right here is a graph which has a downward sloping trend, which is what's expected as the position goes down in the negative direction as time increases. Moving on to my computational model. I wrote the code in Python using GlowScript. As you see the initial conditions of the model, I set the mass of the paper ball to 0.005 to more closely match the mass of a paper ball. I also set the original position of the ball to 000 and the initial velocity of the ball to 000. Here is an excerpt of code from my first computational model. Since the drag force formula was not applied in this model, I set the proportionality constant to 0. And in calculating the force due to gravity, I assume no drag by setting the net force to just be equal to the weight of the ball. Now, the computational model with the drag force has a few key differences. One being that the proportionality constant is not 0. I set it to 0.015, a value I calculated through trial and error until the model predicted a final position equal to that of the observed motion. Another key difference is that the net force now includes both the force due to gravity and the drag force. You can see where I've calculated the drag force and included it in the net force. Here's the graph incorporating the results of the observed motion and the two models. First, let's compare the observed motion to the computational model without drag. The computational model begins to deviate almost immediately from the observed motion of the box, over predicting the box's position for the entire time period. This can be explained in terms of the drag force which is absent from this model. Now let's compare the observed motion to the computational model with drag. In this model, I've chosen the proportionality constant such that the final positions predicted by these two models are equal. Once again, the model overpredicts the object position, except this time it does so in the middle sectors, which can't clearly be seen because I use many points when drawing the graph. This can also be explained in terms of the drag force. So what probably happened was that the drag force was larger than expected at the start, possibly since the object was so light and it became more aerodynamic and was less affected by the drag force. To answer our first question, a terminal velocity is reached when the drag force is equal and opposite to the weight, and only the second model factored in the drag force, and hence this is the only one that predicted a terminal velocity. In the fact that on the graph, the red line does begin to somewhat flatten out and become increasingly linear, suggesting that the object is approaching its terminal velocity. For our second question, An object's terminal velocity depends solely on the velocity needed for the drag force to be equal and opposite to its weight. What velocity the object starts at is irrelevant, and it will simply approach the terminal velocity in the same way. Although from a different initial velocity, an object's terminal velocity is generally specific to the object and is not dependent upon its initial velocity. Thank you for your time.